The information explosion. Tremendous amounts of information to be communicated, to be processed, to be stored. Lightwave technology, transmitting the greatest volume of error-free information, the greatest distance, with minimal signal loss. Light, photonics. Join me now as we journey through the technology of photonics to learn how light energy is used in telecommunications. Photonics is the science and technology of light phenomena. You could say that the photon is to Lightguide fibers what the electron is to copper wire. Today, we will compare photonics, or light physics, to electronics in widespread use for telecommunications. We'll show how these technologies are all related to the same basic phenomena. Basically, a telephone consists of three elements: the transmitter, which converts sound waves into electrical waves, the conductive medium, which carries the electric signal, and a receiver, which converts the electric wave impulses back into sound. Although voice information goes into the system as analog signals, today's transmissions are often converted to digital signals for increased efficiency and because of customer demand for increased services. Like the basic electrical telephone, a light wave system consists of three similar elements: the source, where digital electronic impulses are converted into pulses of light. Photons, or light energy, are then transmitted through a medium, the Lightguide glass fiber, to a light-sensitive detector. The detector converts light back into electricity. It's easy to think of light wave transmission as a separate system to electrical telecommunications. Not so. The light wave system is really a continuation of the same concepts and principles found in the original telephone. Because light wave transmissions are digital, it doesn't matter what information is transmitted. More than voice, the digital signals can be data, image, or any combination. Furthermore, a single fiber can carry thousands of circuits simultaneously. It is important to think of light, or light waves, in the same terms as electrical waves. They're both part of the same system of radiated energy found along the electromagnetic spectrum. And we're all familiar with that narrow band of the spectrum that we call visible light, the rainbow. But the total spectrum is really much broader. The shortwave bands, including ultraviolet, X-rays, gamma rays, all the way to the extremely short cosmic rays, and the long wave bands, infrared, microwave, radio waves, to the very long electric waves. And that's where we find the traditional telecommunications media: electricity, radio, and microwaves. Light, radio signals, X-rays, all radiation is emitted in waves. Now, these waves travel through space at the same velocity, 300 million meters a second. Since they all move at the same rate, the shorter wavelengths move more waves through the same point within a given period of time, and the longer wavelengths move fewer waves through the same point within a given period of time. Electromagnetic wavelengths are measured in meters, or fractions of meters. Their frequencies are determined by the number of complete waves in 1 second. Each complete wave is considered a cycle. Frequencies are expressed in cycles per second, or hertz. Light wave telecommunications operate close to visible light in the infrared band. They are located between the visible spectrum and radio waves. Light waves for telecommunications have wavelengths of between 800 nanometers and 1500 nanometers. A nanometer is a billionth of a meter. Although invisible, infrared waves share those properties of visible light that allow them to pass through glass. Just as copper technology is based on the behavior of electrons, Lightguide technology is based on the photon, or photonics. A photon is a quantum of electromagnetic energy. That is, the smallest indivisible unit of electromagnetic energy. It has no mass, no charge, and an indefinite lifetime. Photons are infinitely smaller than electrons, yet they transmit a great deal of energy. Radiation results when energy is applied to mass. Simply put, the applied energy causes the mass to expand its boundaries momentarily. The mass could be a molecule, an atom, even an electron. When the expanded mass snaps back to its original boundaries, photons are released. Once released, photons travel freely through space at a constant velocity. We think about light waves as rays of energy, vectors that travel in a straight line, but this is not totally the case. All radiation spreads as it moves further from the source, like the effects of a pebble dropped into a pond. The waves keep spreading as the signal moves further from the source. This spreading, or dispersion, is critical to sending light waves through a glass fiber. In order to operate efficiently, the light waves must remain as coherent as possible. The construction of the fiber itself helps to keep the light pulses from scattering. To recap then, photonics is the science of photons, which are the basic particles of all radiation. Photons and the resulting waves travel at a uniform velocity in fairly constant direction, subject to a natural spreading or dispersion. Understanding how these waves behave in a medium like glass, then, is the key to understanding Lightguide. The medium of transmission for light wave signals is called Lightguide. We call it that because each glass fiber guides the light waves from the source to the detector. Actually, there are two groups of Lightguide fiber, single mode and multimode. Single mode fiber is the more efficient technology for error-free transmission over long distances. Multimode fiber offers excellent transmission characteristics specifically for limited applications. The glass fiber guides the light along its very narrow path with a minimum of loss. The challenge then becomes not one of whether light can travel through glass, we know that it can, but holding the shape and energy of its signal over long distances. And this is where single mode fiber excels. Let's take a closer look at how this is accomplished. Starting with the Lightguide fiber itself. Lightguide fiber is comprised of four basic layers. At the center is the glass core. Light wave signals are propagated or transmitted through this microscopically thin core. The core of the fiber is more dense than the cladding. This difference in density between the core and the cladding is the key to propagating light waves down the length of the glass fiber. A polymeric coating surrounds the glass cladding. This consists of a soft inner layer to cushion the glass fiber, plus a harder outer layer to protect the entire package from abrasions. Although light waves travel through space at a constant speed, they travel more slowly through denser media, such as air, glass, and water. Not only do they move more slowly, each wavelength moves at different rates through different material. And when they move from one material into another of a different density, some of the angular rays change direction. And we call this effect refraction. In fact, that's why your face looks distorted when you look through a fishbowl or a water cooler. Another visible example of refraction occurs when light passes at an angle through glass or water and back again into air. We see a rainbow of colors. Now, this happens because each wavelength passes through the prism at slightly different speeds. Therefore, each wavelength is bent or refracted at a slightly different angle. There is no refraction nor reflection when light approaches perpendicular to the boundary. It passes straight through. But when light approaches at any angle, a portion of the ray is refracted and a portion is reflected. As light approaches closer to the boundary, the angle of refraction becomes greater. Eventually, the refracted beam lines up with the boundary and any light beams approaching the boundary at less than this angle are totally reflected. Now let's look at how refraction and reflection are applied to guide a beam of light along a length of glass fiber. The core of the fiber is more dense than the cladding. So a beam of light approaching the boundary between the core and the cladding will be either refracted into the cladding or reflected back into the core, depending upon its angle. A beam of light entering the core within this angle will be reflected down into the core. This is called the angle of acceptance. Since the core is round, the angle of acceptance becomes a cone, the cone of acceptance. In Lightguide fiber, the cone of acceptance ranges from 13 degrees for single-mode fiber to 28 degrees for multi-mode. Beams of light approaching the core at a greater angle will be refracted into the cladding, where its energy is eventually lost through absorption or radiation. That is how light waves travel down a length of fiber. But the telecommunications issue is more complex than merely propagating light energy through fiber cable. We want the greatest volume of information traveling the greatest distance with minimal signal loss. So in talking about light wave communications, you'll hear two terms over and over: loss and bandwidth. First, let's look at signal loss. Some loss occurs even before the light waves enter the Lightguide fiber. Part of that is coupling loss, a small portion of the light energy that simply does not get into the fiber. The beam width of the source also determines just how much energy really gets propagated through the fiber. There are only two primary sources of light for light wave systems. First, light-emitting diodes, called LEDs, and second, injection laser diodes, or ILDs. LEDs have a beam width of 80 degrees. Only a fraction, 13 to 28 degrees of that beam, can be accepted by the Lightguide fiber, which means most of that light energy is lost before it even gets into the Lightguide fiber. Laser beams from ILDs have a beam width of 20 degrees or less. They're more focused and coherent, and therefore more efficient. So, except for some coupling loss, most of the light from an ILD can be accepted for propagation through the fiber. Now, I say can be accepted because the diameter of the core also affects the energy accepted. More energy can be accepted by larger core openings, but fibers with wide core diameters are not efficient for other reasons. The more significant loss factor is attenuation. Attenuation is the loss of light energy propagated through the fiber. It's caused by many factors. One factor is called Rayleigh scattering. This occurs when a glass molecule has an irregular shape. The light wave passing through that irregular molecule will lose its form and energy. Another factor is hydroxyl absorption. Hydroxyl ions are impurities in the glass that soak up light energy, especially at the 1400 nanometer wavelength. Other factors of attenuation include micro bends in the core. They can cause some angular rays to be refracted into the cladding. Impurities other than the hydroxyl ion also absorb energy. Irregularities, bubbles, and bends in the cladding all contribute to attenuation. Attenuation is least likely to occur at two specific bands of wavelength in today's Lightguide fiber. Those bands are located near 1300 nanometers and between 1500 and 1600 nanometers. Notice the peak of signal loss at 1400 nanometers. That's due to the hydroxyl absorption we just mentioned. Although these are the most efficient ranges for light wave transmission, early technology was limited to the 800 to 900 nanometer range, and many effective light wave systems are still operating in this transmission range. A signal loss is tied to specific wavelengths. As we've just seen, those loss characteristics are different at various points on the spectrum. So, when we talk about low loss fiber characteristics, we're looking at two things. One, the signal loss that occurs at the coupling, either between the source and the fiber or between two spliced lengths of fiber, or two, attenuation, which is energy loss within the fiber itself. Because loss characteristics occur at precise wavelengths, these characteristics are a very important aspect of Lightguide specifications. Well, now that we've looked at loss characteristics, let's look at the other aspect of transmission efficiency, bandwidth. Bandwidth characteristics deal with the volume of information that can be transmitted over the Lightguide cable. But fiber bandwidth is more than just the rate of information. The distance that a digital signal can be transmitted without error is also important. And so fiber bandwidth is expressed in megahertz times kilometers. The first generation of Lightguide fibers were only multimode. One important factor limiting bandwidth in multimode fibers is modal dispersion. Light rays that enter multimode fiber parallel to the fiber's axis continue through the fiber in a parallel path. Rays entering at an angle would be propagated, bouncing from side to side. As a result, they travel farther. In fact, each ray takes a slightly different path or mode. Modal dispersion occurs because each mode arrives at the detector at a slightly different time. As a result, the signal coming out of the system is flatter and broader than when it went in. This is modal dispersion, and it limits the rate at which signals can be transmitted to avoid impulse overlap, which could result in transmission errors. There are a number of ways we can enhance bandwidth by overcoming aspects of modal dispersion. You might assume that longer lengths of fiber always have lower bandwidths. Not altogether true. If we used a single length of fiber, that might be true. But Lightguide fibers are almost always spliced, and splicing fiber reduces the degree of modal dispersion. Another way to overcome modal dispersion has to do with core density. In graded index fiber, the core consists of many layers of glass, each with a slightly different density. As a result, the beams that take the longer paths travel faster through the length of fiber, so each mode reaches the detector nearly simultaneously. Graded index fibers have bandwidths of up to 1,300 megahertz kilometers. That's 200 times greater bandwidth than first-generation multimode fibers. But the real solution to the problem of modal dispersion is single-mode fiber. It has a core that is 1/5 to 1/6 the diameter of multimode fiber. Its cone of acceptance is less than half. Most important, single-mode fiber propagates light beams over a single path parallel with the fiber axis, thereby eliminating the effects of modal dispersion. The fiber bandwidth of single-mode fiber is virtually unlimited. The capacity is limited only by the electronics and laser technology, and breakthroughs in that technology are occurring at a very rapid rate. In fact, new records in laboratory transmissions are probably being set even as I speak. As single-frequency laser diodes are perfected, they can raise the available bandwidths of single-mode fiber close to the theoretical potential. Today's investment in single-mode Lightguide fiber will continue to pay increased dividends of expanded capacity with every advance in laser technology. Today, we've taken a good look at the science of photonics and what it means to telecommunications. We've examined such terms as photon, mode, loss, and bandwidth as they are applied to lightwave technology. As you can see, lightwave technology is really an extension of electric telephone technology. It's also an important key to the network of the future. The wideband capabilities of lightwave technology provide a graceful evolution to universal information services. The evolution which began with the concept of universal telephone service in 1908. Universal information services, so that network providers everywhere can give any customer any kind of voice, data, or image service in any place, at any time, in any combination, with maximum convenience and economy. Telecommunications have evolved along a spectrum of technology of which lightwave systems are just one more band, just as light waves are another band on the electromagnetic spectrum.